Okay, so here we are talking about the concepts for college algebra. We're talking about section 3.3, talking about a way to compare linear functions and tables and values to values from exponentials. So if we take a look at the information that was given to us and the way that the information was presented, we can talk about a couple different things. Number one, we can talk about average rate of change. There were two things that were presented really as ways to kind of differentiate uh, linear functions and linear tables and linear information, linear pieces of information. One was average rate of change, one was percent rate of change. For average rate of change, they got really mathy, but essentially average rate of change was slope. Anytime you hear average rate of change, just think slope. What is slope? y2 minus y1 over x2 minus x1, and essentially that was what they gave us in the textbook. They called it f of x plus 1 minus f of x over x plus 1 minus x. But essentially, the average rate of change, anytime you hear average rate of change, just think slope. Percent rate of change, essentially, when you think of rate of change, percent rate of change, think of r. Think of the variable r, our r. The rate is just r. That's essentially what we're going to try and calculate when we calculate percent rate of change. So, for example, if we have a piece of information that is, let's see, I'll set up two different graphs. Not great, not perfect. One will be linear, just like we had. Hopefully this one, yes, that'll be green. This one will be, let's say, red. So, that should have been red, but sorry about that. If we have average rate of change, if we're looking for average rate of change, and we compare, I guess if we're going to compare these two pieces of information, these two graphs, average rate of change, if we calculate the average rate of change for the green, average rate of change between that point and that point, let's say I call it point A and point B, would be some slope. Looks like right here, slope m is about 1. And if we have a whole bunch of data points in our table, A, B, C, D, E, etc., we could have a whole bunch of data points. Essentially, all these data points would come into a table. So if we set up a table like this, x and y, if our slope is 1, let's say we go back, let's say we start here at 0, comma 3. That would be point, let's say that would be f, 0, comma 3. Point C would be maybe, if we're going a slope 1, C would be maybe 1, 4. D would be 2, 5. E would be 3, 6. Just based on what a slope would be. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. That would be the slope. So if we took a look at the average rate of change for this set of data points, and I was given a set of data points, I could say, let's compare. Is it linear? Is it exponential? That's essentially what average rate of change does versus percent rate of change. Is it linear? Is it exponential? You'd say the slope for this would be 4 minus 3, 1, over 1 minus 0, 1. Slope m is 4 minus 3 over 1 minus 0 equals 1. Slope between these 2 points, 5 minus 4 over 2 minus 1 equals 1. Slope m equals 1. For these set of points, 6 minus slope m equals 6 minus 5 over 3 minus 2 equals 1 over 1 equals 1. All the slopes are the same. So for a linear set of data, our average rate of change, our slope, is 1. It's always the same. So if you wanted to differentiate between a linear set of data or an exponential set of data, you could simply look at the slopes of all sets of points, or even two sets of points, sorry. One set of points, two set of points. If the slope is the same for each one of them, then or for both sets of points, then you know that it's linear. If we go over here and we say, well, let's see, I'm going to change to black. Hang on a second. If I've got a point here, and a point there, and a point there, and a point there, and we could say, you know what, let's find the slope between these 2 points. If I draw a line between those 2 points, what's the slope of that one? What's the slope of those 2 points? What's the slope of those 2 points? We can see already that the slope is not going to be the same. The slope will not be the same for, let me erase some data down here so I can get maybe some space. Slope would not be the same for any of these data points. So if I had an xy table, here's my xy table, and again we'd have points 0, maybe 3, 1, let's say my a is 2, 1, 6, 2, 12, 3, 24. What I could do is say, well, if I'm going to differentiate between these two sets of data, is my black set of data linear? If it were linear, I could take the slope of these two, slope m equals 6 minus 3 over 1 minus 0 equals 3 over 1, 3. Let's take a look at the second set of data. Slope here, and this is a way to differentiate. Slope here, 12 minus 6, 12 minus 6 over 2 minus 1 equals 6 over 1 equals 6. Darn it, you know what? Because I calculated the slopes of these two set of points and these two set of points, and it's not the same, this has to be exponential. Exponential, sorry. Because those two slopes are not the same, it has to be exponential, because if we look at this, the line created by those 2 points and the line created by that one and these 2 points, those two slopes are different. Therefore, it has to be, therefore it can't be linear. It has to be exponential. So that's a way, really this is just a way, average rate of change versus percent rate of change is a way to compare whether a set of data is linear, they'd have the same slopes, or the same average rate of change, or exponential. Exponentials do not have the same average rate of change because the slopes are always changing.